Hey, what up, friends? Today we're going to talk about our first day of operations with complex numbers. And just as a background information, like why do we care about complex numbers? How do they fit into our progression? All that good stuff. We just have kind of some random quadratic formula work here. So I remind you of the quadratic formula. And let's say we're trying to solve this thing. And we're thinking about, well, if I tried to factor that, right, what numbers would multiply to positive 5 but add to negative 4? There just simply wouldn't be any, right? If I wanted positive 5 and negative 4, that'd be a negative 5 and a positive 1. But that doesn't multiply to positive 5, right? So if I switch the signs, then they don't. So it's not going to work out. So we would be forced to use the quadratic formula, right? And we're doing that, blah, blah, blah. And then we get stuck right here, because we get the square root of a negative 4. And that's a contradiction to us, because we know that by definition, the square root means I need to take something and multiply it by itself. So whatever's in each of these boxes needs to be the same number. And I'm trying to get a negative 4 out as an answer. So like obviously 2 and 2 wouldn't work, because 2 times 2 is 4, not negative 4. But then if I put a negative in there and they both have to be the same, right? Negative 2 times negative 2 is still a positive 4. The only way to get it to be a negative 4 is if the numbers were different. But that's the complete contradiction of the square root. So up until this point in class, we've been saying, well, that means there's no real solutions. We can't find a real number that does that. Well, that's why we have imaginary numbers. Now, imaginary numbers don't mean that they do not exist. We know they have to exist. So it's just a word that kind of unfortunately has a bad name in English when it translates to math. But when we say there's no real solution, that means there's this one type of number that's not a solution. Just like some answers aren't fractions or some answers are only integers. There's no answers to this that are a real number, but there are answers that are a different type of number, which are imaginary numbers. So what we've done is we've figured out conceptually what that has to be, right? I know that if I want to multiply two things in a row, let's say to get negative 1, we had to define what that number was. We know by definition it's the square root of negative 1, because the square root of anything times itself just undoes that square, right? So we had to make this number up. So the square root of 1 we defined as I. So then by definition, if I take a square root and multiply it by itself, it undoes the square root. So I squared is equal to negative 1. So what I would say this first most important part of today's lesson is the memorization of I is the square root of negative 1, and I squared is equal to negative 1. So the first thing we would do is just learn how to solve with these imaginary numbers. And the good thing is we already have some background of using our product property of roots. In other words, if two numbers are multiplied under one square root, we can just multiply those numbers under their own square roots. So like if we jump into example number 1, if I wanted to isolate x, we'd have to undo the square with a square root. And we know whenever we undo a square with a square root, we do need to use a plus or minus sign. And then we have the square root of negative 13. Now, the only thing that's different when dealing with imaginary numbers when we're doing our real numbers is we just want to separate the negative from the number. So we're going to use that product property of square roots. So I'd rewrite negative 13 as negative 1 times 13. So then if there's two numbers multiplied under one square root, they can each have their own. And then when we see the symbol, the square root of negative 1, we replace that with I. So this number, I root 13, and we could break it up and say this is either I root 13, or we could say it's negative I root 13. We could check that, right? Well, we'll check that later. Let's just keep moving. If we go to the next one, again, we're trying to solve, so we need to isolate x. So we'd subtract 11. And then to undo the square, we would use the square root. And when we square root both sides, we have to introduce a plus or a minus. Now, just like we would have done before, let's separate the negative out of that square root. So we'll rewrite negative 8 as negative 1 times 8. So we can separate them each into their own square roots. And then when we see the square root of negative 1, we replace that with an I. But now, just like you normally would, the square root of 8 can be broken down even further, right? We could simplify that using the product property again. That's root 2 and root 4. So when we rewrite this, the square root of 4 is 2. So we'd put that 2 before the I. So this is the solution to that equation. And then just this last one's just more of the same, right? We'd subtract 11, divide by 2, undo the square with the square root. And then what you can get better at is you can kind of show a few less steps, like I can split them up right away. And then I can start saying square root of -1 is I, and instead of 24, I can do root 4 and root 6. So that's where I get plus or minus 2I root 6. So that's just kind of your nuts and bolts of simplifying the radicals that are negative, and really what we're seeing there is we're just taking the -1 away from the problem, turning it into an I, and then simplifying the remaining product. This is now just definitions to help us talk about things. Whenever we talk about numbers that have I's, they're going to be called, in most cases, complex numbers. So complex numbers, complex comes from a combination of moving parts, something that's complex, like problems that are complex have a lot of different things going on, or maybe like societal issues are complex because there's a lot of different opinions coming together. So that's why we call these complex numbers, and they're always in the form of A plus BI, where this first number is a real number, and then the thing that comes after that is an imaginary number. And again, that word complex comes from different parts being put together. Like a complex problem has a lot of different parts. So this number has different parts, so we call them complex. When we categorize numbers, and you can just kind of write down this example here, we just want to know like what type of numbers are what. I might suggest that you pull out your number sets homework, or like number sets notes from Unit 1. Because we did this big thing where we had like a sheet of paper and then we split it and we said we had all these circles and like these were the imaginary numbers. But what we put on top of it was complex, meaning like anything we do in our number system is going to be complex. So all of these numbers are labeled as complex because they are complex. All the numbers that we work with are complex. And again, that's why I might point you back to Unit 1 notes. But after that, we can be more specific. So this is a complex number to begin with, but because it has an imaginary component, it is also an imaginary number. And that's why we can see the imaginary numbers are under the complex. Whereas the -8, it is complex because all of our numbers are complex, but there is no imaginary portion. So it's just the real portion. So it's just this side, so it's only real. So if a complex number has an imaginary component, it's complex and imaginary. If a complex number only has the real component, then it's complex and just real. Then you'll note this one doesn't have the real component. So it's still complex because all of our numbers are complex. But if there's no real component, to be more specific, we call it a pure imaginary. And this last one just indicating that if somebody took the time to put an I in their answer, even if it was 0 I's, we are still going to consider that to be imaginary as well because they took the time to write it with an I. So more so just definitions of our number sets, but then also in general, what I want you to know when we're writing complex numbers, we always want to write them in that order. So put the real part first if there is one, and then the imaginary part second. So the last part of our focus for today is going to be operations involving I. So we're going to talk about addition, subtraction, and then multiplication and division. So when it comes to addition and subtraction, just think like terms. Like, for instance, if this question over here was something you were working on, you'd be like, okay, well, there's no need for the parentheses, so let's just collect all that we have. So like +5 and +8, those numbers should combine to be another number. And then we see we have some x's. So the +7x's here should combine with the -11x's there. And when we combine them, we get -4x. So you're just treating the numbers as like terms and the x's as like terms. We're going to do the same thing with i's. We can notice that there's nothing in front of the parentheses, so I could just rewrite it without the parentheses. So we see the same thing, right? We have these numbers, 5 and 8, so the numbers should combine to be another number. And then we have these i's. We have 7 of them there and -11 of them there. So they should also combine to be i's, negative 4i. So I'm just kind of asking you to look at the similarities between how we wrote it with an I versus how you've done it with an X before. So letter B is just more practice. You can pause the video, practice on your own, and then that was what the answer would have been. When it comes to subtraction, do exactly what you normally would, distribute the negative. So like this first parentheses doesn't have anything in front of it. So when I distribute the negative, the opposite of a negative 6 is a positive 6. And the opposite of positive 5i would be negative 5i. Once you distribute the negative, again, do the same thing. The numbers, so combine the real aspects, right? Real numbers are like terms with real numbers. So that'd be negative 7. And then the imaginary components will be like to themselves because imaginary and imaginary should be imaginary. So 8 i's, and if I took away 5 i's, I'd only have positive 3 i's remaining. And then if you wanted to practice letter D, just another subtraction, pause the video, and that would have been your answer. The next operation is multiplication. And my biggest advice here is to show many steps, show a lot of steps. So you'll see what I mean. First, I want you to multiply and actually put I squared in your answer. Then rewrite your answer, substituting I squared with negative 1, and then finally simplify. So let's see how that looks. So we're going to use our distributive property. So 4 times 5 is 20. And then 4 times negative 7i would be negative 28i. We'll distribute the next term. 3i times 5. 3 times 5 is 15, and then there's an I there. Now at the end, we're going to multiply the numbers. So 3 and negative 7 is negative 21, and then I times I would be I squared. So that's what I mean in your first step, you should use I squared. Then what I recommend is substituting. What I mean by that is I squared, so I'm just rewriting the problem. We said at the beginning that we had to memorize that I squared was just a different way of writing the number negative 1. So in other words, when I see that symbol, I want to replace it with an empty set of parentheses so I can fill it in with what it's equal to. If I squared is equal to negative 1, wherever I see that symbol, I replace it with a set of parentheses and put in a negative 21. Then you can simplify to get your final answer. So we have 20. These are like terms because they're both i's. And then negative 21 times negative 1 is positive 21. So then finally I can see 20 and 21 would combine to 41, and then we have minus 13i. And you'll notice that we wrote that in the format of a complex number where the real part was first and the imaginary part was second. So that's how we do multiplication. Letter F is more of the same. If you want to practice that, please pause the video, and then you can check your answer with me. Now, the last operation for today, we're going to be talking about when there's a division. So this is just a little side information. Like we know from before that we're not allowed to have square roots in the denominator of a fraction. And a lot of times you've seen directions that say something like rationalize the denominator. So there was 2 types of examples we saw with that when we were working on them. Like example number 1 was when we just had one term in the denominator. It's like we can't have the square root of 3, so we get creative and we multiply by 1 because we know any number times 1 is still itself. It might look different, like for example, 1/2, if I multiply the top and the bottom by 2/2, which is just 1, I get 2/4. It looks different, but that's the same exact value as 1/2. So we know when there's only one term in the denominator, we can simply multiply that by its own square roots on the top and the bottom. So root 3 times root 3, by definition, is 3. So then we've successfully rewrote this fraction without the square root on the bottom, but it has the same value. The other type of problem that we've seen is when there's 2 terms in the denominator. So something like 2 minus root 3. When there was 2 terms in the denominator, we had to multiply by that conjugate, which means we took the sign in the middle and just changed it from a negative to a positive, or vice versa, from a positive to a negative. And then if I multiply it on the top and the bottom, I'm not changing the value because that's just a special form of 1. So we know that from before, but what our connection is that I is a square root. So here we have a square root in the denominator, right? Now, I wouldn't rewrite it this way, but we could see it this way if you wanted to. Instead of I could call that root -1. So whenever we see an I, we know it is a square root, so I'm not allowed to multiply or have a square root in the denominator of a fraction. So if there is a square root in the denominator of a fraction, you just ask yourself, what type is it? Was there one term down there, or were there two of them? So here, I can see that there's only one term. So if there's only one term, I just multiplied by that square root to get rid of it. So like, if I see it with the square roots for a second, the only square root that's in the denominator is root 1. So I'd multiply the top and the bottom by root -1. Now, we just don't work with the square root of -1. We call it an I instead. But you should see that as a square root. So if I go to the original problem, the way that we'd show our work is I'm not allowed to have I on the bottom because I is a square root. So to get rid of a one term on the bottom, you just multiply by that square root. So we distribute, so 4 times I. This would be -7I squared. And then on the bottom, 2 times I would be 2I squared. So you'll notice when I'm multiplying, I still use I squared. Then I substitute I squared with an empty set of parentheses. And then we replace it with its value of -1. And then we simplify. So this would be 4I plus 7 over -2. Now, when the question specifically tells you how to write your answer, then you'll need to follow that. But if I look at this one, it's not technically in complex form. So if I rearrange a little bit and put the 7 first, we know that a fraction, if there's 2 terms on top, that means each of the terms are divided by that numerator or that denominator, right? If things had a common denominator, we would have added the numerators. So if you need to rewrite this not as a fraction, just divide the real number by -2, and then divide the imaginary part by the denominator. And then we can see it look more like that classic complex number form. Now the next type of problem would be something like letter H. And in letter H, what we notice is there's a square root in the bottom. They didn't write it as a square root, they used a different symbol, but we know I is the square root of -1. So this is a square root in the denominator. We're not allowed to have that. So we ask ourselves, well, what type is it? Well, there's 2 terms down there. There's a number 4 and a -5i. So it looks kind of like this when there's 2 terms in the denominator. So if there was 2 terms in the denominator, we multiplied by the conjugate. In other words, whatever sign was here, we just flipped it to the opposite. So we do the same thing here because they're still dealing with square roots. So 4 and 5i, we change the minus to a plus. If I do it to the bottom, I have to do it to the top. Now I encourage you to put in grouping symbols so you know to do the distributive property. And then from here, it just turns into 2 multiplication problems. So we'll distribute the top. So 5 times 4 is 20. 5 times 5i, so 5 times 5, and then an I. 3i times 4, so 3 times 4, and then an I. And then again at the end, 3i times 5i, so 3 times 5 is 15. I times I is I squared. We'll move to the denominator, do the same thing. 4 times 4 is 16. 4 times 5i, so 4 times 5, and then an I. And the inside, -5i times 4, so -5 times 4, and then an I. And then finally, -5i times +5i. Well, -5 times +5, and then I times I. So after we do that, we keep our answer in terms of I squared, so then we can start to replace and simplify. Now I'm going to do a little simplification along the way, meaning in the middle here, 25i and 12i, I can write that as 37i. But then when I get to I squared, before I do anything, I'm always going to replace it with a -1. Same thing on the bottom. There was a 16 there. And this is a way of checking our work. If we use the right conjugate, the i's should go away. So 20i, taking away 20i is nothing. And then I squared goes away because it's just a -1. Now we'll simplify one more time. So 37i minus 15, sorry. And then on the bottom, we have 16 plus 25. So when we collect our like terms, 20, let me do a different color. Numbers with numbers. So 20 minus 15 just results in a 5. And then on top, we also have plus 37i. And on the bottom, we have 16 plus 25, which is simply just 41. And that's what I was saying before. If the directions don't tell you how to write your answer, like maybe you can just leave it like this. If they want it in that complex number form, then you would know how to do that. So those are the examples for today. If you wanted a few more of those practices, you could try I and J, and then you come here for the answers. But those were the notes for today. We'll be talking about graphing and the rest of it on our second day.